Neither of these resonance contributors actually exist. Hey there, OChemNinjas. In this video, we're going to define the resonance hybrid and explain how it's different than resonance contributors. When I look at this molecule, I can draw resonance contributors for this molecule. When I look at this molecule, I see the positive charge is the unhappiest place because it lacks electron density. So I need to draw some arrows that push electron density toward that positive charge. If you're not familiar with the concept of looking at resonance as the unhappiest place, watch the video that I have linked down below that will show you how to draw resonance contributors by finding the unhappiest place in the molecule. The carbon with the positive charge is the unhappiest place. It lacks electron density. It wants more electrons, so we should push electrons towards it. Like from where? Like from this pi bond. I can take the 2 electrons in this pi bond and swing them over in a bond-to-bond arrow. That would form a pi bond between carbons 1 and 2, and that would form a new positive charge on carbon 3. By moving the electrons over, we had to take electrons away from carbon 3, so carbon 3 now has a positive charge, and that is the completion of the resonance series for this molecule. The important thing we need to say about this resonance series is to ask ourselves the question, which of these resonance contributors actually exists? And the answer is very important. Neither of these resonance contributors actually exists. Neither of these resonance contributors actually exists. This is not 2 different structures drawn on the screen. This is 1 molecule drawn twice. The resonance arrow here means that these are resonance contributors. This is not an equilibrium arrow. These 2 molecules are not in equilibrium with each other. It's not sometimes this one, sometimes this one. It is not oscillating back and forth. The positive charge is not sometimes on carbon 1, sometimes on carbon 3. These are not unique structures. Neither of these structures actually exists. And that brings us to the point of the video. The only thing that exists is the resonance hybrid. So what is the resonance hybrid? Before we get there, let me clear up one other confusing point. Some of you might be saying, well, aren't these the same molecule though? Aren't these just pancake flips of each other? Can't we just take this molecule and flip it over and it becomes the other molecule? I mean, yes, in this example, technically you could, but that's not what we're saying here. That's not what I'm saying. I'm not saying that these are pancake flips of each other. If that were true, if these were just pancake flips of each other, if these were really the same molecule, then we'd have a discrete single bond and a discrete double bond. And we know that single bonds are longer in length than double bonds. So we should be able to measure the bond lengths of this molecule, and we should see 2 different bond lengths if these are in fact the same structure. But it's actually really cool. What we find when we measure the bond lengths of these molecules is that neither bond has the bond length we would expect. The single bond is not as long as we would expect for a single bond, and the double bond is not as short as we would expect for a double bond. Instead, the bond lengths for both of these bonds are exactly the same, and they're exactly in between the bond length of a single and a double bond. These 2 bond lengths have the same bond length intermediate between a single and a double bond, and that's the reason that we know that these are not oscillating back and forth. If they were, then we'd have discrete bond lengths, but because the bond lengths are the same, neither of these molecules exists. Because these bond lengths are the same, that tells us that the only thing that exists is the resonance hybrid. So let's go ahead and define and draw the resonance hybrid. Sorry, one more thing. I keep cutting myself off. Another way I can prove to you that these are not pancake flips is if I were to draw another methyl group on the molecule. Now, these are clearly not pancake flips, and these are clearly unique structures, even though neither of these structures would actually exist. Okay, finally, the resonance hybrid. The resonance hybrid is a weighted average of all of the contributing resonance contributors. It's an amalgamation of all of these structures into one structure that's neither structure individually, but it's a weighted average, a composite of all of these different resonance contributors. We start with the carbon backbone. I'm going to go back to just the 3 carbon backbone for the rest of this example. And remember what I told you earlier, both of these bonds have the same bond length, and it's intermediate between the bond length of a single and a double bond. So how do we draw that in the resonance hybrid? It's not a pure double bond, and it's not a pure pi bond. So what we do is we draw a partial pi bond. We draw a dotted line to show that this is a partial pi bond between carbons 1 and 2, and a partial pi bond between carbons 2 and 3. In these resonance contributors, the pi bond is between carbon 2 and 3 in one contributor and between 1 and 2 in the other contributor. So the resonance hybrid demonstrates that with partial pi bonds between carbons 1 and 2 and carbons 2 and 3. The same is true with the positive charge. The positive charge is distributed between carbon 1 and carbon 3, but it's not on any one carbon at any given time. Instead, it's intermediate between them. There's not a full positive charge on carbon 1 or carbon 3. Instead, what we do is we draw a partial positive charge. We use this Greek lowercase letter delta to show a partial positive charge on carbon 1 and a partial positive charge on carbon 3. Collectively, we have one full positive charge. It's just distributed between carbon 1 and carbon 3. And this is the resonance hybrid. This is the weighted average of these 2 resonance contributors. It shows the partial pi bond between the 2 bonds, and it shows the partial positive charge between carbons 1 and 3. Notice we didn't draw any resonance contributors that put a positive charge on carbon number 2, so carbon number 2 remains neutral in our resonance hybrid. There's no partial charge on carbon number 2. I keep using this term weighted average. I haven't really talked about that yet. We look at each of these resonance contributors, and there are a set of rules that help us figure out which one contributes more or less to the resonance hybrid. That's not the subject of this video. I have an entire separate video on ranking resonance contributors, but since these two structures are otherwise identical, both of these structures weight the same towards this resonance hybrid, so we're not going to get into that in this video. Now, this weighted average resonance hybrid is kind of cumbersome to draw. It's the only thing that exists, but it's a bit of a pain to draw. So chemists rarely draw the resonance hybrid unless there's a reason to highlight it for whatever reason. Instead, we draw one of the resonance contributors, or sometimes the entire resonance series. Whichever resonance contributor is important for whatever point we're trying to make, that's the resonance contributor we draw. But in the back of our head, we always remember that this structure does not actually exist. It is the resonance hybrid that exists. We can draw various resonance contributors, but neither of these resonance contributors actually exist. We have to remember that when we draw resonance structures. So as your instructor lectures throughout the course, your instructor will draw one of the resonance contributors and probably rarely draw the resonance hybrid, but you still need to understand what the resonance hybrid means and how we can interconvert between these resonance contributors. Neither resonance contributor exists. The only thing that exists is the resonance hybrid.
Thanks for training with us today, ninjas. Check out this other content to see if you can level up even further. As always, don't forget to like and subscribe.